Hello, everyone. Today we're going to be talking about the Jeans Criterion and nuclear fusion. Let's get right into it. So, in this lesson, we're going to specifically be talking about the criterion that is necessary for the formation of stars from nebulae, specifically called the Jeans Criterion. We're also going to be going into a bit more detail about the fusion that occurs inside stellar cores on the main sequence. Stars that are outside the main sequence we'll talk about later. Um, but we're going to go more in depth with this idea of fusion, more so than we have in the past. So first, let's jump right into the Jeans criterion. So as we've talked about before, stars are first formed in interstellar clouds of dust and gas called nebulae. And these nebulae can exist for millions of years in relative equilibrium. Some gas might, enter or exit the cloud, but overall, we're in a state of equilibrium. But eventually, something is going to happen that disturbs this equilibrium. This could be a nearby supernova that creates a shock wave that disrupts this equilibrium in the gas cloud. It could be a collision with another nebula, for example. Um, so, yeah, this equilibrium is not going to be forever. It's eventually going to be thrown off balance. And this disturbance causes the cloud to become unstable and possibly collapse. When this cloud collapses, it can form stars. And we can also measure the temperature of these nebulae with their spectra, with their absorption and emission spectra. Um, and that's going to be important for this Jeans criterion that tells us if a star can be formed from a nebula or not. So the Jeans criterion tells us that there's enough mass in the gas cloud in the nebula for gravity to overcome radiation pressure and to start the process of fusion that creates stars. Now, if we look at a cloud of this interstellar gas, the energy in this cloud is a combination of both kinetic energy and potential energy of the particles. And if we think back to our work with fields, remember when two objects interact gravitationally, the closer they get, the more negative the potential energy, the gravitational potential energy is between them. So if you consider an infinite distance away from a planet to be the zero line for gravitational energy, then if you bring an object close to that planet, it's going to lose gravitational energy and that energy will become negative. So at an infinite separation, again, there's no potential energy, and those particles only have kinetic energy. And when the magnitude of the potential energy is greater than the kinetic energy, remember magnitude we're using here because we don't want to worry about that negative sign. But if the magnitude of that potential energy is greater than the kinetic energy, then we meet the Jeans criterion, and we can have a star form. So getting into more specifics about the Jeans criterion, so if you've got a cold, dense gas, that's actually far more likely to collapse than a hot, low-density gas. And again, that's because a hot, low-density gas has a lot more kinetic energy, and the particles are farther apart. If you have a low-density gas, the particles are more diffuse, they're more spread out. So there's going to be less potential energy between those less magnitude of potential energy between those particles. And that's not what we want in order to get the gas to collapse and form a star. So typically a cooler, dense gas, so lower kinetic energy, a higher magnitude of potential energy is going to give us a higher chance at meeting the Jeans criterion. So typically a cool cloud has a density of about 3 times 10 to the 7 particles per meter cubed and a temperature of about 100 Kelvin. So not as cool as interstellar space, but relatively cool when it comes to other objects in the universe. So with these specific conditions, the Jeans mass, which is the minimum mass needed for a star to form, has to be at least 400,000 times the solar mass. And because of this incredibly large mass relative to the sun, often we get stars forming in clusters. And these stars can have masses of 1.5 to 500 times the solar mass. So these large nebulae with very large masses, again, can cause multiple stars to form within the nebula. And there are also other gas clouds that are hotter, that are cooler and have even higher densities. And these types of gas clouds, these nebulae with, again, cooler temperatures and higher densities, these are what lead to the formation of these larger, brighter stars. So think about 10 to the 11 particles per cubic meter and 10 Kelvin instead of the given values here. You're going to get brighter stars, you're going to get bigger stars in that situation. Okay, so now we're going to look at fusion in sun-like stars, so stars that are similar to the mass of our sun. And these type of stars burn hydrogen in their cores through a fusion reaction called the proton-proton chain. And this reaction has 3 stages. The first stage, we have 2 protons. We can think of them instead in this situation as hydrogen 1 nuclei. And they fuse together into a hydrogen 2 nucleus. And notice a hydrogen 2 nucleus has a mass number of 2. Therefore, instead of 2 protons, we have a proton and a neutron. So one of our protons turns into a neutron, thus emitting a positron and a neutrino. So think back to beta plus decay. And then we have our hydrogen 2 nucleus, also known as deuterium, kind of floating around in the core, and it meets up and fuses with another hydrogen 1 nucleus or a proton, and those two fuse together to create a helium 3 nucleus and a gamma ray photon. And then finally, that helium 3 nucleus meets up with another helium 3 nucleus, and those two fuse together, and we're left with the helium 4 nucleus and 2 more hydrogen 1 nuclei. So overall, we use 6 hydrogen nuclei, and we give back 2 hydrogen nuclei. So therefore, 4 hydrogen nuclei are used in total. So we lose 4 hydrogen nuclei. And there's a nice illustration to show us this reaction as well. We kind of see the stage 1, we have the 2 protons or the 2 hydrogen nuclei fusing into the hydrogen 2 nucleus. And we emit that neutrino and positron. And often that positron will meet another electron in the core and create gamma rays. They'll annihilate, create gamma rays. So we get some energy from that as well. And then our hydrogen 2 nucleus meets with another proton, fuses to helium 3. That helium 3 meets with another helium 3, helium 4, and 2 protons. Okay, so now we have fusion in larger mass stars, and this reaction is going to be slightly different from our proton-proton chain. This reaction is called a CNO cycle because carbon, nitrogen, and oxygen are all involved in this reaction. And this process only occurs in stars with core temperatures of at least 2 times 10 to the 7 Kelvin. So very hot temperatures relative to our sun. So this is what our reaction looks like. So we start off with a proton or a hydrogen nucleus fusing with a carbon-12 nucleus. And that gives us nitrogen-13, which is unstable. And we also get a gamma ray that's produced as well, some energy that's produced from this fusion reaction. And then we have nitrogen-13, and that undergoes positron decay into carbon-13. So it emits a positron and a neutrino, and also we are left with carbon-13. Then carbon-13 then fuses with another proton, and it gives us nitrogen-14 and a gamma ray photon, so nitrogen-14 and some energy. Then that nitrogen-14 again fuses with another proton, and we get oxygen-15, and oxygen-15, just like nitrogen-13, is unstable, so it's going to decay as well. So oxygen-15 undergoes positron decay, releases a positron, a neutrino, and we're left with nitrogen-15. And then finally, nitrogen-15 fuses with another proton. And when that happens, we get a carbon-12 nucleus and a helium-4 nucleus. So we can see overall in this reaction, we use 4 protons. And carbon-12 is both a piece of the starting of this reaction, the fuel, and it's also a product at the same time. So we use 1 carbon-12, and we also release 1 carbon-12 nucleus. Okay, and overall we can see we release 2 neutrinos, 3 gamma ray photons, and 2 positrons throughout this entire process. So there is a decent amount of energy released in this process. So again, just to wrap this up, this type of fusion, either the CNO cycle or the proton-proton cycle, these are examples of hydrogen fusion, and hydrogen fusion takes up the majority of a star's lifetime until, as we've said before, it starts fusing more heavier elements. So that's all I have for you today. I hope you enjoyed, and I'll see you next time.